All right. So today what we're going to focus on is 6.2. Our next test will be 6.2, 6.3, and probably 6.4. 6.2, we're going to spend 4 days on. It's a big chapter. So we're going to start off with what our today's lesson, which is U substitution. I'll type that out for us. Or I should say that's what most people call it. I don't think the book exactly calls it this, but if you ever Google U substitution of integrals, you'll get what our lesson is today. So today we're going to do U substitution. We'll do 3 practice problems. I'm going to get very few homework problems for tonight. And then the next days we'll get more and more. All right. So U substitution 6.2. All right. So just looking at this right now, we have an integral that's kind of weird right now. We have sine x and e cosine x, and they're being multiplied to each other. So that makes it really difficult because we don't actually know what the antiderivative of this is. We know them separately. Like I know the antiderivative of sine x would be negative cosine. I know the integral of e to the x is e to the x. So is there a way I could use this to my advantage to help out and solve this? Because right now we can't solve it with our current skills. So we have to figure out a way that we could rewrite this into something more reasonable. And this is where U substitution comes in. I have to identify something that I can make simpler in order to solve. So for example, what I'm looking at right now is e cosine x. I don't know what the antiderivative of e cosine x is. I don't know how to get to there. But something I do know is e to the x, because the antiderivative of e to the x is just simply e to the x. So can I rewrite this in any way so it makes it look like e to the x? Well, if I wrote cosine x equals u, that means I could replace this as e to the u. That'd be really nice. But since we're dealing with integrals, when we plug in u, we also need d of u. So it's like the substitution. So before, you need u and what we usually call u prime. For these cases, I'll call it du. But we usually call it u prime. So we need the derivative of this. So if I said cosine x equals u, then the derivative of u, which is considered du, should be the derivative of cosine x. And the derivative of cosine x is negative sine x. Negative sine x, I'm sorry. Always you have to put this when you derive over x, dx. Because if the du is here, then the dx is over here. So I'll just rewrite that as one thing. Negative sine x dx. That dx is not in the sign, okay? Where does the dx come from technically? Because you remember, it's usually when you write a derivative, it's d whatever variable over dx. So we technically multiply the dx on both sides. So dy dx, and then you multiply dx on both sides. Or du dx, you multiply dx on both sides. So your goal is to substitute and change this to u. But you can't just change the value like for fun. So when you change it, you also have to make sure you could change the derivative or the whole integral correctly also. So if I change this right here to u, I need the rest of this integral, including the dx, to turn in some way into looking like this, into this derivative, negative sine x dx. Now my problem is I almost have it. It's sine x dx, but I need negative sine dx. So what I'm going to do is that here, I'm going to add a negative. If you add a negative inside the integral, technically I'm multiplying a negative, then I'm going to divide a negative on the outside of the integral. If you put one on the inside, you have to put one on the outside, so it stays equal. This now, sine x, and the dx over here, this all here is the derivative of du, or du. So I could rewrite negative sine dx into e to the u, that u which I got, and I can make negative sine x dx into du with a little negative on the outside. So I have to figure out what I'm changing to u and then use the derivative to reduce it down to du. Now looking at this integral, the integral of e to the u du, we should all know the antiderivative of e to the u. Or it's the same antiderivative of e to the x. The antiderivative of this is e to the u. So we have a negative on the outside, and its antiderivative e to the u. But we don't want it in terms of u, we want it in terms of x. So I'm going to take this u value and resubstitute my original u value, which was cosine x. So I have negative e to the cosine x. And because this was an indefinite integral, as in it had no bounds, we always got to remember the plus c. At that point, we have simplified as much as possible, and we are done. Sarah?
That came from the e to the cosine x, but what about the sine x that was in front of it?
The sine x that was in front of it turned into, so this sine x dx, turned into du. And when you integrate a d whatever variable, they disappear because they cancel each other out. So what we're left with is the antiderivative of this, e to the u. Now, the interesting thing about e to the u, the antiderivative is exactly the same. We'll do another example where they're not exactly the same, and then you'll see how to do it from there.
So, Mr. T,
yeah, Aria?
How did you put the antiderivative to the thing? You made the antiderivative into an exponent.
The antiderivative. So are you asking what's the antiderivative of e to the u, or?
And you turn the derivative. You turned the cosine x into the derivative. How did you do that?
I didn't turn cosine x to the derivative. I just turned cosine x, and I said it equals a new variable that I'm introducing and that you will introduce, which I called u.
Oh, I see.
So so you're adding that, and then you said, wait a second, if this is going to be a u variable, I need this to be a du variable. And in order to obtain a du variable, I'm going to have to derive u. So then I have to change u into du over dx, which remember is a different way to write u prime. We're used to writing u prime because it's nice and neater. But this du dx is the same as u prime. And then I would just multiply dx on both sides. So then I have my dx on one side and my du on the other. And what that's useful for is that I could plug in here sine x, blah, 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 and make it into a u and disappear, basically. Which is good. You kind of want to just reduce everything and make it disappear as best as you can. I'm happy to take any other questions on this. Now, this U substitution mainly happens because we're multiplying two expressions typically. In here, it was sine x and e cosine x. And because addition and subtraction, you can just separate it and do them separately, which is good. But in this case, we need to be able to do it together. Okay, let's talk about this next one. The integral of x squared times the square root of 5 plus 2x to the third. All right, so we basically have two terms here, x squared and the square root of 5 plus 2x to the third. Your usual goal is to make the u the more complicated one. You want to reduce the hardest question or part of the question into a u. And in this case, the u would be better served for the square root of 5 plus 2x to the third, because it's kind of easy to derive and integrate x squared. If you do it the other way, it makes it a lot harder. So you want to usually go harder to easier. So this is the hardest one. So I'm going to state that, and I'm going to particularly state the inside is 5 plus 2x to the third. And that equals u. You could technically state with the outside. It just makes your antiderivative or your derivative different. Since this is u, and I have a dx here, I can't have a u within the dx. So I'm going to have to make that into a du by deriving it. So I'm going to derive on the left. 5, when you derive 5, it disappears. 2x to the third, you bring it down, then lowered it by 1. So you have 6x to the second. 6x to the second dx. Don't forget the dx. Or the dx will always cancel out, but you should just kind of always remember it. That's proper. All right. So I'm going to rewrite this integral as x squared, the square root of u du, or dx, my bad. I have not made a du yet. Now, my issue is I still have this x squared. Is there a way to change this x squared to the u? Or could I make all this dx's and all these x's into du's? Well, this and this are equal to each other. So I need to make the x squared to look like 6x squared. So what I'm going to do is multiply by a 6 inside the integral. But if I multiply inside the integral, I have to do the opposite outside the integral. So I'm going to divide by 6, or represent it as a fraction 1 over 6. So whatever I do inside, I have to do the opposite outside. If I multiply something, I have to divide it on the outside. Now, 6x squared dx matches exactly with the du we have here. Our integral with a 1/6 hanging on the outside becomes the square root of u du, which is a lot more simpler to deal with than this thing up here, the square root of u du. Now, how do I antiderive the square root of u? Well, I have to change it into u 1/2 power du. Once it's a half a power, once it's on the outside, once it's a half a power, the antiderivative is going to be you add 1 and bring it down, or you add 1, so it's going to be 3 over 2 to the u. Then you divide it by the new number. So 3 over 2 is dividing by 3 over 2. To rewrite that a little bit more cleanly, 1/6 times, when you divide by a fraction, you multiply by the reciprocal, 2u 3/2/3. So I just reciprocated the 3/2. 1, 3. U 3/2 all over 9. So that usually is the hardest part of this is usually deciding what the U is and then making sure you're anti-derived correctly. So we have U 3/2 power all over 9. But we weren't looking at for in terms of U. We need this X value. And our original U was 5 plus 2x cubed. So I'm going to rewrite this. I'll do it over here. 5 plus, 2x cubed to the power of 3/2 all over 9. But don't forget, you integrated by a non-bounded integral. So just put your little plus c there. You could rewrite that as square root to the 3rd power. Not really necessary. You already did all the tough parts. You could just leave it like this. Give you some time to write it. If you have any questions, I don't mind you asking. Okay. We're going to do our last one for today. The integral of cotangent 7x dx. Now, if it was just cotangent x, all you would have to do is do the antiderivative of cotangent x. But because you have the 7x in here, we're going to have to figure out how to break that up in part because we have a cotangent and we have a 7x inside the cotangent, and that makes it a little bit more different. We need to figure out how to antiderive. So my first suggestion, does anyone remember what trig functions, like what combination of sine and cosine makes cotangent? How does it look like? How can I rewrite cotangent as terms of sine and cosine?
Cosine over sine.
Excellent. You could change it into cosine over sine. Now it's cotangent 7x, so it's cosine 7x, and then sine 7x. I guess I could just put it here. Times the dx. ds is technically multiplied, so I'll just put it on top of the fraction. Okay, once we do that, we see two different terms. We're going to try to figure out how to reduce this down because right now we can't really do the antiderivative of cosine over sine with 7x's inside. Let's see. I'm thinking, let's take the sine 7x, which is in the denominator, and reduce that down to u. So I'm going to say sine 7x equals u. So I'm going to derive this. So that's du. So in this case, sine 7x, I need the derivative of sine 7x. Because it's a 7x on the inside, we're going to have to do the chain rule. So sine, the derivative of sine is cosine, 7x, times the derivative of the inside, which is just 7. So those derivative rules we learned 3 to 4 months ago, they still apply, especially chain rule. And I'll just rewrite it for a little bit more neatness. Cosine 7x equals 7 cosine 7x equals du. All right, looking at that, I have a cosine 7x. That's really nice. I have a dx. Oh, I forgot to write dx here. But I have a dx. That's really nice. But I'm missing that 7. So I'm going to have to multiply this thing by 7. When I multiply something inside the integral by 7, I have to do the opposite outside the integral. So that's 1 over 7. So 1 over 7. I could change my sine 7x into u. And I could change all my purple underlined stuff into du. You could also technically write it like this, which might be a little bit more clear. 1 over u du. These are the same thing left and right. Okay. So that is our integral simplified. Now, anyone can speak up. What is the integral of 1 over u or 1 over x? What's the antiderivative of 1 over u? Does anyone remember?
Is it ln?
Good. Good, RA. So the antiderivative of 1 over u, because your instinct is to change it into u negative 1. But if you do that, you end up becoming u0 over 0, and you can't divide by 0. So you should notice something's weird when you do it like that. That means it's that special case ln. So 1 over 7 times ln u. We actually have a value for u, 1 over 7 ln. Inside the ln is sine 7x. That's a u from originally. Don't forget, we integrated without bounds, so plus c. Because it's an ln, you technically can only have positive numbers ln, so you should technically put an absolute value there. You will not be taking points off if you got a question like that, you forgot the absolute value. But technically there should be absolute value there because it is a positive, only positive numbers in there. Okay, so those are our 3 problems. Your homework will be a worksheet today that is based on I'm giving you the u value. You're getting the u value, so you just have to work it out. Tomorrow we'll practice without giving the u value. So we're going to practice finding it ourselves and how do we decide that. But the steps and the operations, that's going to be practiced today for your homework. All right. I don't really have an exit ticket prepared, so you can type here for your attendance, and then you guys are free to go.
Thank you.
No problem.
Thank you.
No problem. No problem.
Thank you.
No sweat. There, she good, man? Are you there?